Welcome to the CGU Earth Data webinar. And today it's our great pleasure to have our speaker, Zhang from ETH. So Ce got his PhD at Stanford University, and he is a very popular person among the geoscientists because people all would like to work with him to do the data mining on field. So with that, I will give the rest time to Ce to show his research, and at the end of it, we'll have some interaction between the speaker and the participants. So there you go.
Okay, great. Hi, everyone. Thank you so much for inviting me here. Just before my talk, I know nothing about geology. I know nothing about paleontology, right? So, but I will try to tell you a little bit about our experience working with experts in this two domain. And hopefully, if there's something that we can help with, just let me know, right? So I think I'm going to talk about two things. The first one is a project called Deep Dive, and also the application of it called the Geo Deep Dive and the Paleo Deep Dive. And that is something we have been working on from 2010 to 2016, right? So this is probably the reason I have the honor to speak here. So, and then I will talk a little bit about things that we have been working on over the years. That is something that after I come to ETH, we start a new project called ETH with a very similar goal as Deep Dive. I will also talk about these two things. So, but first, let's time travel back to 2010, right? So we were at Wisconsin. It's a very cold place. And that's also the time that we realized that many of the scientific problems and also many non-scientific problems afterwards require a more microscopic view of our knowledge. So what do I mean by that? So let's look at this one example, right? So here we have a human, and we have the genome of the human and have certain mutations, right? So inside our body, those kind of genome are going to decide our protein inside our body. And now, given a target drug, right, how can we predict whether this drug could be effective or not, right? So this is a very important problem centered on the topic of personal medicine, right? If you think about this problem, right, so the fundamental question, and one fundamental question that we need to understand is really try to get all those interactions between all those proteins, right? And then we can try to understand if this drug triggers that protein, right? Following all those interactions, we can get some feeling about whether this drug actually works or not. Right. I mean, of course, this is an oversimplified version of this very complex problem, but this is one of the crucial steps. So how can you get all those interactions from protein, right? So back in 2010, our realization is that a lot of people actually try to read those like journal articles all by themselves, try to extract a table that looks like this, contains all those interactions between different proteins. And there's actually one very interesting project called Belgrade. They actually process like 50,000, like 55,000 like different articles. And of course, if you look at PubMed, there are millions of those articles. And there's no way that you can have all those people reading all those all by themselves. So the question that we had back then is it possible for us to build a machine to actually read all those articles automatically? And that is what we have been working on over the years. At the end of the day, we have a single system to actually automatically process 1.3 million articles and automatically populate this something called knowledge base, which is the relationship between different genes. And this is just one application, right? So in terms of paleontology, right? So together with our friends, collaborators, and we start looking to the impact of climate change to biodiversity, right? So that is where we try to compile this biodiversity curve, right? So, and the thing that we want to do is given all those very old documents, how can we automatically process them and try to extract these relations? And of course, there are also a lot of applications in terms of social science, right? How to kind of track human trafficking, right? In the dark web, there's another application that we were building a couple of years ago. So if you put them all together, right? So one key component is really how to do knowledge base construction. Given a whole bunch of documents, how can we extract knowledge out of that? And this is something that we have been working on. Actually, my PhD thesis together with my advisor and also a lot of collaborators. So what are the challenges in building such a system, right? So on one hand, you have your user. So here our target user are those scientists who are not computer scientists, right? But domain scientists. And we have the documents, will be terabytes of documents. So we want to connect them together via machine learning and also distributed systems. So we realize there are actually two challenges. The first challenge is on the usability side, because it's often very painful and often tedious for those users to actually program a machine learning applications back then in 2010, okay? And also how to debug them and how to tune a machine learning system. So that's actually one challenge that we really want to understand. Another challenge is on the scalability side, right? Because we are dealing with terabytes of data with very complex machine learning models, right? We kind of need to scale them up to really understand how can we handle all those data. This actually drives our exploration on the technical side, right? So in the deep dive system, the user is going to write a high-level declarative language that we call a deep dive program, and then it's automatically compile that into a machine learning task without user intervention, and then automatically extract relations. So this is something that we try to enable. So on technical side, right? So we spend a whole bunch of effort in try to understand scalability and performance. And also on the usability side, we're really curious about this loop between feature engineering and training data engineering and the machine learning task. How can we make sure the user can continuously improve the quality of their machine learning applications? That's also a place that we spend a whole bunch of effort there. So at the end of the day, right, if you look at deep dive, it contains the application part and also contains the technical side. So in this talk, let me focus more on the application side. So I will talk about the framework, right? So how did we think about knowledge-based construction almost like 5 years ago? And one application that we constructed using this framework. So the deep dive framework that we developed like 5 years ago contains 3 different phases, right? So the input of the system is all those documents, okay? Could be very old document, could be new document, could be scanned document, could be PDF, right? So all those input documents that human can read, but machine cannot. And then there's a whole bunch of external knowledge bases that people have already assembled, right? Wikipedia, Freebase, right? So all the name of cities on the planet, right? All those knowledge. So the first phase of the system is really try to deal with feature extractions, right? The user is going to write a whole bunch of feature extractors to actually process all those input data into a semi-structured form. And then try to give us more rules to deal with supervision, to actually generate some training example, and also give us some rules to deal with domain knowledge. I'm going to talk about this in more detail later, right? But at the end of the day, it gave you a probabilistic graphical model, contains a whole bunch of random variables and their relationships. Right? So, and after that, so we have the statistical inference phase that take as input all those supervision data and all those domain knowledge rules and try to automatically extract relationships out of those documents. So that is the end-to-end process. So we can go deeper into each of the phases, right? So for the first phase, it's about feature extraction. Back then, deep learning wasn't that popular like 10 years ago, right? So our view on this is if you give me a sentence look like this, if you want a machine to extract information out of it, right, you can actually extract a whole bunch of features from this sentence. For example, you can use some standard tool like Stanford NLP, right? You can actually say, yeah, so I know Michelle Obama is actually a person, right? So that's a very important feature for the machine to know, right? President is a title, right? Or you can write some user-defined functions to extract relationships, right? For example, you can say, okay, so there are actually 2 people here, right? Michelle Obama, Barack Obama, right? So they are actually connected by the verb married, right? And then this becomes a feature that machine is aware of. So at the end of the day, right, so all the documents are stored as a table like this, right? So you can actually have a high-level domain-specific language to automatically extract those tables like this. But you can think about this as input, which is a document, and output a whole bunch of database tables contains features. Given those features, right, the second step is really try to understand how can we associate those features with the prediction that we want to make, right? In this example, whether we can extract the relationship that Barack Obama and Michelle Obama are spouse, right? So given this, right, so you need to make this association. So there are 2 different ways you can actually associate them. The first one is by generating training examples, right? You can say, yeah, so I have a rule where if the 2 people are connected by the verb married, I know for sure, highly likely they are married, right? So then you can actually generate those high confidence training examples, right, from your features. So another way is you can actually generate some of the domain knowledge, right? For example, you say, yeah, so I know has spouse is a symmetric relationship, right? In the sense that if person A is married to person B, then person B must be married to person A, right? So in the knowledge base, you must have this symmetric relationship, right? You can also write a rule to say, yeah, so in the output, yeah, So these two random variables, each one corresponding to one of those predictions, either must be true at the same time or must be false at the same time, right? So you can also introduce those type of rules into the system, and then you have kind of a public graphical model, and then after that you can actually do learning, do inference to extract relationships out of this. So this is just the high level framework, right? So and then you can actually apply that to different applications. So one application that we played with is about paleontology, right? So here, this is the 4 different type of extractions that we support, right? So you can actually extract information from natural language text, right? Or from tables, even from document layout. That's actually something I learned from our collaborators. And also there's some extraction you can have from images, right? You can actually connect this like with a name, right? And also reason about the size of this, right? So this is actually 4 types of things that we have been doing. So all following the framework that I was talking about. So at the end of the day, it's like 3,000 lines of Python and SQL queries. And on some very specific relations, we can actually get the human level quality extractions. Now you can actually compare that with some existing database that people have been compiling over the years, right? For example, there's one database called FatalDB, right? So that's created by human paleontologists, right? So I think they took them like 300 years, like 300 geoscientists for 8 years to read 50,000 documents, right? And extract 1 million relations, right? Which is impressive, right? So a lot of hard work goes into this. So if you have automatic system, right? So you can actually have automatic created database with higher than 90% precision, right? And it's not that expensive, right? So it only takes like 2,000 cores for like 46 machine years, right? So but the whole thing finished in like 2 weeks, right? So it can actually automatically kind of read like 300,000 documents and give you more relations, right? So and if you look at the scientific insight coming out of the system, right, it's kind of consistent with what like human have, right? So on some relations, it's kind of even can achieve sometimes better precision as professional human volunteers. So, and what's more impressive is because it's done by machine, right? You can really scale it up rapidly, right? So even though we have like 46 machine years to run, right? So given 2,000 cores, the whole thing actually finished in a week. Right? So this is actually a quick demo from the system, and we can actually quickly watch this video together, right, for you to get a sense about what we have here.
Yeah, there are several seconds of delay, so no problem.
Between Shannon Peters' Geoscience Research Group, Milo Lipney's Condor Research Group, and the Hazy Research Group. The goal is to help geoscientists extract data that is buried in the text, tables, and figures, journal articles, and websites, sometimes called dark data. To bring dark data to light, we use the Hazy Research Group's machine reading system. The Geo Deep Dive system extends a database created by Professor Peters' group called MacroStrat. MacroStrat contains information about rock formations and individual geographical units. Here is an example, the Barnett Formation. The Barnett Formation contains several units that are spatially distributed as shown on the map. It is also temporally distributed over several geological time intervals. MacroStrat contains over 36,000 rock formation units like these. There is also geologically relevant information in journal articles like this one. As we'll see, Geo Deep Dive extracts information about these rock formations from journal articles. As of today, Geo Deep Dive has processed over 36,000 research papers. This is the Geo Deep Dive homepage. It shows a summary of the results of Geo Deep Dive's deep linguistic and statistical processing. Geo Deep Dive has 2 main goals. First, organize the literature around the MacroStrat database to create a spatio-temporal index of the geology literature. On the left-hand side, we organize the extraction results spatially on a map. Our second goal is to augment the MacroStrat database by extracting dark data. On the right-hand side, we list some global statistics. For example, we found about 500,000 mentions of formation units from 36,000 documents and about 24,000 measurements of the units. Let's walk through an example of how a geoscientist may use GeoDeep dive. Suppose the geologist is interested in the first unit, the Barnett Formation at Fort Worth Basin. We can navigate to that unit from here. Just as on MacroStrat, GeoDeep dive reports 8 units in this formation. Each unit is characterized by a polygon on the map, and their canonical names are listed in this table. We also show the extraction results for each unit, including the number of mentions, documents, and measurements. Suppose the geologist is interested in the first unit, the Barnett Formation at Fort Worth Basin. We can navigate to that unit from here. This is the page for the unit of the Barnett Formation in the Fort Worth Basin. On the left-hand side, we embed a page from the MacroStrat database. In the sidebar on the right-hand side, we show some statistics about GeoDeep dive's extractions for this unit. For example, the estimated total organic carbon, or TOC, is about 6%. This information does not exist in MacroStrat. Instead, it is aggregated by GeoDeep dive from dark data, that is, the data buried in the text and figures in journal articles. The geologist can dive deeper into how this number is produced. Here, we have organized the extracted measurements along different dimensions, including time and space. Suppose our geologist wants to dive into the temporal dimension. By clicking here, she is presented with a list of time intervals for which GeoDeep dive has found extractions. Here, Pennsylvanian and Assagian. Click on the first button, and GeoDeep dive will load all the extraction details about the Barnett Formation at Fort Worth Basin and in the Pennsylvanian time interval. Each row in this table is one measurement extraction. We show the annotated textual evidence for each piece. The geologist can go through them and provide feedback on their correctness. For instance, the first extraction appears correct, and so we click yes. Such feedback helps GeoDeep dive improve itself over time. We can dive even deeper into the document context of the sentence. This is GeoDeep dive's document browser. A journal paper is anonymized by the different types of entities it mentions, as well as colorful annotations for these mentions. Move the mouse cursor to hover on one of the mentions, and you will see a box containing further information about this mention. Here are 3 kinds of probabilistic predictions about this Barnett Shale mention. Notice that Fort Worth is not mentioned in the surrounding text. Using a rich variety of signals and background knowledge, GeoDeep dive determined that this text referred to the Barnett Formation located at Fort Worth Basin, and not, for example, any of the other 7 units in this formation. The geologist can provide feedback for these predictions as well. GeoDeep dive is a quickly evolving project, and we have been continuously expanding our
Yeah, so this is just a quick kind of overview of essentially what we have done, like applying deep dive to one of the applications, right? So, and that was 2016, right? So this is what we are doing from 2010 to 2016, which I also think is probably the reason that I get the honor to talk about this today to you guys, right? So, but another thing that we need to realize is this is like 2016, right? It's like 5 years ago. A lot of things have changed since then. So we see the kind of development of deep learning, right? When we develop deep dive, there's actually there's deep learning, but not that famous, like not that popular, right? So, and also we see faster and faster hardware. So now let me tell a little bit about what we have been working on after 2016, right? So our realization is, although there are a lot of things have changed. So if you look at this picture, right? So from the user to the technology in the usability angle, and also from technology to the hardware on the scalability angle, we actually see that this fundamental challenge has not changed over the years, even though the technology have been rapidly developing over the years. So that actually inspired a whole bunch of follow-up projects that we have after we finish up the deep dive project. So essentially, if you look at how users are building kind of machine learning system today, right? So over the years, we see actually two interesting trends. So on one hand, you see the continued democratization of machine learning, right? So that's actually something we have been looking at over the years, and you start to see machine learning models are being applied to more and more applications developed by more and more people. The consequence of that is if you look at the background for those people, they become more and more like domain scientists, which is great because they know the application and they care about the application. But they, on the other hand, inevitably, they start to get less computer science and machine learning background. So essentially, you have more and more people, but each user, if you judge in their computer science background, also become less powerful. But on the other hand, you also see the complexity of building machine learning applications start to decrease, start to increasing. It's increasing way beyond what we can imagine when we were building deep dive. So there's kind of hardware become more diverse, right? So the data ecosystem also become more diverse. Instead of all the data in a database system, the data today is everywhere, right? So you start to see machine learning technology continue to develop, right? And also there's also the additional regulation requirement going beyond have something with good accuracy, right? Into worry about fairness, worry about robustness, right? Which is a good thing, right? But on the other hand, it's also make the complexity of building machine learning applications kind of harder and harder. So if you look at this, right, if you look at all of our users and together with all the tools that we are providing to those users, I think it's fair to say that today it's never been easier for someone to get some machine learning model out of the machine learning system, right? But on the other hand, is that really the right machine learning model? Is that a good machine learning model, right? So this question gets harder and harder to answer. And also giving a machine learning model that you are not happy with, right? So how can you improve such a model? And this question also become harder and harder to answer. So this actually two questions inspired the things that we have been working on since 2016 after we built up the deep dive system. One thing that we have been looking at is really how to continue to scale up the training of machine learning systems, right? So on the other hand, how can we enable a data-centric development and operational framework such that everyone who have some knowledge in their specific domain can build machine learning applications all by themselves. So on the first part, right, so we kind of look at how should the machine communicate when you want to have hundreds of machines to train a single machine learning system, right, play with this, and how can you integrate that into different data ecosystems, right? So at some point, right, if any one of you want to train machine learning model inside the database, right, or want to train those like really big models like this, we just train a model with like 100 trillion parameters, for example, right? So let me know, right? We know a little bit about that. So, but the second, probably more relevant today, is another thing I've been looking at is really how to provide the user a systematic step-by-step guideline for the development process of machine learning. And the goal is really try to make sure everyone who wants to do machine learning can do machine learning. But that's not an easy task because given the complexity of the machine learning ecosystem, if you just give, for example, a biologist, right, so machine learning system, highly likely the outcome will not be ideal, right? So what we have been working on is really an end-to-end process to really get the user through the ML dev and ML ops journey, right? So from the data side as an input, right? So we kind of worry about how to do parsing, how to do augmentation, right? And how to do automatic feasibility study, and how to automatically give user guidance about where to acquire labels and how to do data cleaning, right? After you have the machine learning autonomous system in the middle, right? How can you do continuous integration of the model? How can you do domain drifting protection of the model, right? And how can you close the loop between model monitoring and the model development, right? So if you look at this, right, so there are actually two different loops, right? So one loop is how to continuously improve the model quality, right? You have your first model, right? You get your first set of extractions. Highly likely you will not be happy about those, right? So the question that we want to understand is how can we help the user to improve the data quality such that they can get a better machine learning model after, like down the road. And second is more like the model cycle, right? After you get a sequence of models, you need to continue to test it, to adapt it, right? Like how can you deal with that? So one observation is both sides are actually kind of data centric, right? But in different ways. So today, let me tell a little bit about on the data side, about things that we know a little bit how to do. So the first thing is actually related to deep dive. That's actually something we were thinking about. What are the remaining challenge after we know how to extract, some of the relations from text, right? So, and then we kind of realize there's a hidden challenge, right? If you go back to this picture that I showed before, right? You have this input source, you have this internal knowledge base, you try to extract features, right? Sounds very simple. But there's a hidden challenge somewhere. That is, if you input at PDFs, or if you input at those very old documents, or even new documents with like text-based PDF, they are actually very hard to deal with, because those formats are actually designed to be human readable, but not really machine readable, right? So if you like have a PDF file there, if you really look at the structure of how they store data, right, it's very hard for you to find, this place a figure or this place a table, right? Inside this table, where are columns, where are the rows, right? All those information, even though we as a human can understand them, even though the machine really needs that to extract information, right? So they are actually not there in the document. So this probably gave you one of the least discussed challenge about information extraction, but in our experience, it's one of the top bottleneck in getting things done, right? So essentially the thing that we want to understand is take as input a document look like this. How can you recover the structure, right? How can I know this thing is a caption, this thing is a table, these are different cells, right? And also how can we take this view and translate that into, for example, XML file, right? That you can actually write your feature extractor on, okay? So that's actually something that we were trying to understand in this project after we finished the deep dive thing. So we thought it would be very easy, right? So our high level idea is, okay, so we need to have training data for this. But luckily for scientific documents, right? So we do have the source code for many of those. So how about we just download all the article, like all the millions of articles on archive, and try to take the source file to generate this automatically, right? We can type that through a PDF, like a tag kind of compiler, generate the PDF. We can use sig tag to generate the structure, and then we can train a machine learning model using that. So this is a high level idea, right? So essentially at the end of the day, what we have is really kind of one generator for kind of biased labels about document structure, right? On the left-hand side, you have the training data. On the right-hand side, you have the labels, right? And then you try to automatically learn a machine learning model to reverse the structure, right? That's a given kind of a document on the left-hand side. How can you recover the structure on the right-hand side, right? So this is something that we know a little bit about how to do, that we have been working on for years. So at the end of the day, in terms of system, right, I won't go into detail, but at the high level, if you want to recover document structure, we know how to do that up to 90% accuracy for most of the elements for scientific documents, okay? So if you find this useful, let me know, right? So we are more than happy to work together to try to see essentially how we can help. So by essentially, if you put this together with the deep dive projects, you start to have an end-to-end journey of information extraction. So another thing that we have been looking at is really try to understand how can we do data acquisition and data cleaning to improve your model, right? So assuming you have a deep dive system and then you have your first batch of extractions out of a document, highly likely the system is missing something and highly likely the system is getting some prediction wrong, right? So here the question is, okay, what I do next, right? So I get my first machine learning model, which is great, but it's not good enough. How can I improve my machine learning model to get the better quality, right? Either fairness or accuracy or robustness, etc. So here, right, so improve your machine learning model. there are two different ways, right? You can keep twisting your model to make that better and better, right? Which is very useful in many cases. But at least an equally important thing to do is to improve your data, to get more data, to clean up your data. And then the question is, okay, so I have millions of documents that I could label. Which one should I label, right? If there are some noise in my data that I can clean up, which one should I clean up, right? So that's actually something that we have been looking at, and we know a little bit about what to do. So essentially, here's the problem that we kind of understand a little bit. That is, you have a training set. The training set could have a whole bunch of problems, right? There could be missing value, there could be noise, right? You pipe that through a machine learning training process, and you get to a machine learning model. And then there's some metrics of this machine learning model, maybe the validation accuracy, maybe the fairness, something you are not happy about, okay? So there are two questions that we kind of look at over the years. The first question is out of those data problems, which one should I fix to improve my final utility? The second question is out of all the training examples, right? So if for example, fairness of the model is not good enough, which example should I blame, right? Which example is the reason that the model is not good enough? So people have been working on this for a while, right? So for the first question, you can actually measure the entropy over the noise, right? Alter some gradient-based method. For the second one, you can compute, for example, Shapley value or expected margin improvement to get some information about what's the problem in your data. So once you have this, you can actually enable a whole bunch of use cases, right? For example, if you have a training set with some incorrect labels, right? So here, the cat is labeled as a dog, right? The fish is labeled as a cat, right? If you pipe them to your machine learning training pipeline, right? Highly likely your accuracy could suffer on some of the examples, right? So here the question, okay, I really want to find out which training example has the wrong label, right? How can we systematically do that? Another thing, for example, you have a training data set, right? So, and it's kind of unbalanced. There's some population, you have a lot of training example. You have some population that you don't have that many training example, right? So, and also like in geo deep dive, right? We also say, yeah, in that country, we have a lot of example. In that country, we don't have that many, right? So in this case, you could have a fairness issue, right? If you just take that data set and train a model on it. So here again, the question is, okay, how can we really kind of identify those like overly represented examples that we can actually remove them, right? Or how can we identify those like underrepresented populations that we can acquire more data from, right? So this is actually another use case if you can know how to debug your data. There's also some security consequences, right? For example, one interesting way to attack a machine learning model during the training process is you can actually put some of the like backdoor into your images, right? So here for the second image, I put this 3 different rectangles into the image, right? If you just train a machine learning model using it, and during testing time, right, you give that with the same, you give a different image with the same pattern, right? So in many cases, you can actually show, you can actually attack the model to actually make a wrong prediction on this image as long as there's such a pattern there, right? So the question is, okay, so if I know my system is vulnerable, right, how can we find out those training examples with backdoor patterns? So all of this actually relies on the ability to actually try to understand this training process and try to debug your data given this training process. So people have been working on this for a while, right? So but what is the kind of challenge here, right? So challenge is that this is what people have been working on, but it's not really what real world machine learning applications actually looks like, right? So if you look at real world machine learning applications, they often, it's like a piece of code that looks like this, right? So the part of it deal with the machine learning side, and then there's another part of it try to deal with feature extraction, right? So the fundamental question is we don't really know how to understand these 2 components together, right? So from the computer science side, we are actually lacking the fundamental understanding about how to connect those like feature extractor and the machine learning models to do end-to-end data debugging. So that is something that we know a little bit about, right? So we have been working on understanding this type of machine learning pipelines for a while, try to understand what's the impact of data noise and what's the impact of data examples, and essentially how to compute these fundamental quantities as fast as possible, right? So I won't go into the technical detail here, right? But essentially you can actually construct a simple proxy pipelines, right? That's kind of easier to analyze compared with the original pipeline. And you can actually, for different type of kind of feature extractions, pipelines, you can have different proxies. But what's more important is it actually works pretty well. Okay, so if you have a data set with incorrect labels, right? So once you can do is you can actually take those like compute the Sharpie value, right, of each of the training example, and then you kind of pick the pick the one that has the lowest value, and then try to manually fix the label. Okay, so if you do this, the benefit is if you pick randomly which label to fix, right? So you are going to, you're going to have more like better and better accuracy. Okay, so more you fix, the better you have, right? Once you fix everything, it's perfect, right? So, and then if you kind of prioritize which one to fix, right? So you can actually have more effective labeling process, right? For them, you can fix like only 30% of your data set, those wrong labels. But on the other hand, you can actually get like really good accuracy down the road. Another thing is, for example, if you have like those kind of like unfairness, like in this application, right? You could automatically try to extract which population is underrepresented or kind of overrepresented, right? So you can either add in data or removing data. This is actually way more effective compared with randomly adding data points, right? So this is another thing that we know a little bit about how to do. So this is actually another thing that we have been working on over the years, right? It's really try to understand how can we systematically build up those every single components for end-to-end machine learning journey. Okay, so this is actually all I have for today, right? So again, I know almost nothing about the geology, right? So, but on the other hand, we have been looking at how to build a machine learning system to enable that domain expert build the machine application over the time for years. So if you guys see any potential that we can work together, right, just let me know. I'm really more than happy to help, right? So otherwise, I'm happy to answer whatever question you guys may have. Yeah, thank you.
Great, thank you very much, sir, for your great talk. And now it's time for questions from our participants. So you could either open your mic to ask a question, or you could also pose a question, and I will read it on your behalf. Okay, so here's a question from Hai Ying. Very good talk. I have two questions. And the first one, how do you extract the relationship between two entities, for example, fossils and formation, if this information in different sentences?
Yeah, so that's a very good question. So you are talking about essentially the scope of relation extraction, right? So the easiest way is you for the sentence scope, and that's always it's not easy, but easier, right? If you are cross sentence, it actually depends on how far away they are. Okay, so if they are in the same paragraph, you can actually maintain like some memory of the sentences, right? You can say, after reading the sentence, here's my memory, right? And then you can actually engineer the whole system like this. We also see cases where the whole thing is really far away. Okay, so there's a one sentence in the beginning, there's one sentence at the end of the document that's like 3 or 4 pages apart from each other. In that case, back then we do not have a good way of dealing with that. But today, if you have those deep learning models, right, you can actually train a document level LSTM to help you, right? So I think back then we don't have a good idea. We have some ad hoc solutions, right, which are not that beautiful. But today I think you can do way better than what we have been doing in deep dive. Yeah. So
okay.
I guess
so now,
I get.
Okay. Okay. I will read the second question: that how do you construct a knowledge graph? I think knowledge base or just external base.
Yeah, so essentially what we have been doing is and you can think about the whole thing like a rolling a snowball, right? So you get some of the external knowledge base, right? People have been working on that for a while. They have some knowledge about what's there. And then you kind of use them to generate training examples, right? You know what's inside that is true, right? You can actually automatically generate some labels. And then you train your system, you can get more examples and you have some human look at them and filter them out. You get a larger knowledge base. And then you can actually use that to extract even more information, right? So that's actually a standard process people are doing for information extraction. You kind of keep growing kind of this knowledge base, right? So that is what we have done. Right? So I'm not sure I can answer your question or not. Yeah.
Okay, the next question is from Wen Ying, and it's a question about the weak supervision. And they said that the active learning and weak supervision are two important technologies in data centric machine learning systems, but nowadays the big pre-training data, train a massive and label data works well with many tasks, and active learning weak supervision seems doesn't work as good as expected. So what do you think about this phenomenon? And do you have any thoughts about the future research directions about active learning and weak supervision to incorporate more human or experts prior knowledge?
Yeah. So I think this is a very good question, very insightful. That's also the thing that we have been thinking about, like asking ourselves every day about what are we doing, right? Let me tell you my opinion, right? I again, I mean, I'm this less technical, but more like my personal opinion about this, right? So on one hand, I don't think these three different technologies, like the pre-trained model, weak supervision, and also those active learning things, right? I don't think they are exclusive in any way, right? So they actually try to bring down the cost of building machine applications from different angles. On one hand, those pre-trained model really save you a lot of effort in collecting data, right? You can actually use other tasks, like as some training example, right? So for this task, you can transfer those data, right? So, which is great, right? But on the other hand, when you become, when you go to the phase, you need to fine tune your model on a given task, right? Inevitably, you get to the question about, okay, on this new domain, right? How can I get my label, right? And then that goes to active learning, goes to weak supervision, right? So again, right? So I don't think they will solve all of your problems, right? But we do see in many cases, they will lower the cost, right? So I think if your expectation is active learning and weak supervision going to lower the cost in some way, I think you'll be a very satisfied user of today's technology, right? If your expectation is, so they are going to give me some way to solve all my problems, I don't think so, right? So like about the future research directions, one thing that we have been looking at is really how to combine all of this, right? Because I don't think that exclusive. One project we have been working on is you mentioned about pre-trained models, right? So, but there are so many pre-trained models, right? If you go to TensorFlow Hub, there are maybe like 100 different image models, right? Some of them are trained on this data set, some of them are trained on that data set, right? One question is, okay, which one should I fine tune? Which one should I use? I can't use all of them, it's very expensive. One thing you could do is you can actually combine active learning with this, right? You can actually say, okay, how can I collect my data in a smart way such that with maybe 20 or 60 labels, I can distinguish which pre-trained model perform better on my target task. Oh, that's a lot of fun. It's kind of like a lot of interesting can happen there, right? So similarly for weak supervision, right? So how can you develop a weak supervision system knowing that you must transfer from that 100 different embeddings, right? So which I think that's super cool. And also about human prior, right? So there's always two things. Human can provide knowledge in terms of logical rules, right? There's a whole bunch of people working on those like neurosymbolic system, right? You have a neural network and you have some logical rules, right? So I think that's really fascinating. So on the other hand, human can also give feedback at a label level, try to write rules for like generate training data, or try to fix the labels, try to clean your data, right? So I think at the end of the day, what's really interesting down the road is to build a centralized scheduler for human attention, right? In the sense that, okay, I have 20 people, this is their skill. Some know how to write code for this, some know how to label stuff, right? So how can I automatically allocate their attention and their time to improve my my target accuracy or fairness as fast as possible, right? So I think that is very interesting, right? So you make a very good point that some of the technology cannot fix all your problems. What I think is interesting is, now let's put all of them together, have a pool of technologies, and then try to automatically decide which one to use, right? And which so I think that's interesting in my opinion. Yeah. Sorry for the long answer. I don't know whether that's make you more confusing or make you less confused. Yeah. Yeah.
Okay, it's great to hear your thoughts. So next question, please. Okay, I have quite a naive question, but I'm quite curious about it. That from my perspective, that once we go to the advanced stage of the weak artificial intelligence, that we might reach a day where computers could recommend scientists with certain good science questions that we work at. But not only based on knowledge graph, but that we currently have, but also based on the database that is available in the community. For example, in the Paleo deep dive, for example, in the sedimentary geochemistry and Paleontology project leading by Stanford University, for example. And whether it is possible, or what's your perspective on it, that someday that the model, the computer will tell us, okay, this could not be explained by the model, and there are such relationships, and it's very likely to be a very promising science questions that you should check it out. So at least in the shopping business, online shopping now, we already achieved that, but that's a relatively simple task. But for science question, that will fundamentally change the way that scientists to look for a question to begin working. So what do you think about that?
Oh yeah, I mean, and that's an interesting question, right? So I mean, about automatic hypothesis forming, right? So I think and there are a lot of people working on this, right? So like if you look at a lot of papers about those like pharmaceutical applications, right? People try to find what is a promising drug, right? Those automatic drug design, right? You can think about that as some form of hypothesis forming, right? So there are also people, like even for geology, right? So like what is the most promising like location, right? I mean, I should look at for this question, right? So I think if in the context of knowledge base, right? So if you can phrase your question or phrase your hypothesis to say, yeah, my hypothesis is what is the possible relationship between the two entities, right? People know a little bit about how to do that, right? If your view of automatic hypothesis, the generation is more open-ended, right? To say, I don't know what the form of hypothesis you are going to give me. I just want a statement from the machine telling me, okay, this is something you should look at. Oh, that's very hard. I have no idea how to do that. But if you can phrase your question as knowledge-based completion, right? Not creation, it's not extraction, but giving an incomplete knowledge base, try to recommend a potential candidate that could be true. That people know a little bit about how to do, given a high quality knowledge base to start with.
Okay, next question, please. Okay, I have a question. So what's your perspective on deep shovel?
Sorry, what?
So have you? Yeah, I suppose that you know the product that produced by Shanghai Jiaotong University.
Yeah, I know. Yeah. So I know a little bit, but I don't know too much. I'm actually really excited today to learn about it from you guys. Yeah, I also try to understand how we can help. Yeah, yeah. So like to me, it's fascinating, right? Yeah, but I don't know too deeply about that, and I'm really looking forward to learn. Yeah.
Are there any participants? Yeah, are there anyone that are part of shovel? Maybe you can open your mic or type to share your opinions. Actually, I do like one of their product that actually my own group used. In your talk that you mostly talk about either image data identification, for example, language related, but for geochemists, including the sedimentary geochemists at Stanford University, that we are really interested in the tablets because we wouldn't actually know in what age of a rock with a particular different composition. So that's all in the table. So either requires the transfer of the image of tables to the HTML format. So Deep Shovel, I think I do like one of the product is that they use the geoscience publications to train that model, and therefore to detect that which page has the corresponding table that you might want, and this might be the format that you want to extract it. So people could extract it to the Excel format then could move on with that. So I really like it. And although there are similar products that are in the market, for example, Microsoft or WPS, actually to our surprise, the QQ is quite good at that for identifying the tables, tablet information.
Oh yeah.
Yeah.
That's also what I heard, right? So like we have friends who are more close to that, and I'm really impressed like by the quality of that, right? And a very ambitious goal, and I'm sure it's going to be great, right? So yeah.
Because in Hangzhou, actually, I happen to encounter with several people who run small businesses where they specialize in doing this because they do have the app. For example, for middle school teachers, for example, physics teacher or a mathematics teacher would like to convert a PDF version into a Word version, for example. So something on the people doing that, but still it's pretty hard because there are a lot of science.
Yeah, it's super hard. I mean, it's super hard. That part is super hard. That's actually we spend like that's pretty much like what this system trying to do, right? So like you have a document, right? I want to say, yeah, this is a table, right? As you can see, we are missing the last row, even in the demo, right? So it's very hard. I mean, also for scientific articles, that's actually super hard because scientists are very creative in creating beer tables. Yeah, so there are a lot of tables that that's not that easy to parse. Doing that well is really hard, right? So, and that's why I'm really impressed by the quality, like what you are achieving today.
I do agree with you, especially for geochemists. We really would like to create a new ways to present a table, and it's quite common. You put the first column as iron, second column as nickel, and then put the third column iron divided by nickel ratio. And then have the fourth column. Then that creates a lot of problems when doing it. Suddenly have two iron in your table. Once it extraction. Okay, there's another question about the Shapley value here. Is it used locally or globally?
Oh yeah, for the Shapley value, so essentially what we are doing is we treat every single data example as a player, right? And then you try to measure the improvement of the utility, right? So you put it in or take it out, right? So, and then you try to calculate expectation over all the possible ways to arrange other tuples. I'm not sure about local or global in what context. If you are thinking about like whether it's local explanation or global explanation, one thing is we do Shapley for training. So I don't think it's fit too well into the current terminology of local explanation, global explanation. But I would say that's local, right? Because you are computing the essentially sensitivity of that example, right? Yeah. Cool.
Okay.
Great.
Okay.
Yeah.
Okay. Do you have more questions from our participants? If no, then let's end our seminar now. And it's about 1 hour, so it's great. And thank you very much, sir, for a great talk. And thanks everyone for your participation. And the next talk will be 7 days from now. So we will have next speaker from Rajasthan University to talk about the geological questions about the large igneous provinces and the surface climate. Okay, with that, thanks everyone. And Zhang, have a good day.
Thank you. Bye.